What's going on, everybody? Welcome back from your break. I'm going to start with this. What you're going to notice with this video is I am not trying to be perfect. I just want to put something out for you guys. And I'm going to be looking down at my notes. I'm going to see what I want to talk to you about. I know where I want to go, but at the same time, I don't know exactly what I want to say, how I want to say it. I'm going to kind of just do it. We're going to get back into the swing of things with doing some of these videos. And I wanted to put the first one out about our physics that we're going to be moving into. So this is like the first lesson that I want to put out for you guys. I also want to use it to review the measuring motion packet. All right, cool. So let's do this. All right. So first of all, what is physics? Physics is the branch of science that deals with matter and its motion, and also how matter interacts with energy and forces to make it change its motion, that kind of thing. We are going to focus primarily on energy, forces, and motion when we're dealing with physics. So let's get into those three things and the definition and a little bit of explanation. All right, so first of all, energy. Energy is something's ability to do work. It is how things change and move. Something's ability to do work, change, and move. That's what energy is. So if you think about when we've been talking about energy from the beginning of the year, and we talked about energy as related to the molecule dance. Oh, okay. All right. The molecule dance. So take out your molecules. Let me see what I got here for it. All right. All right. All right. Take out your molecules. All right. So we have the solid, right? It has a certain amount of energy, right? And you see it's in motion, right? Give it more energy. It has more motion. There you go. And we got more. Yeah. Listen, for all of you that didn't want to do this in class, I understand because we're all watching you, but nobody's watching you now. You can do it now. I mean, except for that camera that your parents set up secretly in your room to make sure that you're not getting into trouble. I mean, except for that, nobody else can see you, right? All right, cool. All right, so that's energy. Going back to the molecules and how molecules move, they move more when they have more energy. And we said that the more energy that the molecules have, it increases the heat, the temperature, that kind of thing. All right, so there's energy. Forces. A force is a push or a pull on something. A push or a pull is a force. A force will cause an object to accelerate, decelerate, which means slow down. It will cause objects to remain in place. You saw that on that worksheet that you guys were doing. We'll talk about that. Or it can change shape or direction. So it can make something change shape or direction. So again, let me say that again. Forces. A force is a push or a pull. It causes an object to accelerate, slow down, remain in place, change shape or direction. That's what a force is. And then we have motion. A motion is simply a change in an object's position, where it is. And then think about things that we've already talked about when we did some of the warm-ups from before break. How do we know an object is in motion? All right, I'm going to give you a second to think about that. How do we know an object is in motion? Good. We know an object is in motion because we have a reference point. We can see where the object is in relation to that reference point. So we'll talk more about that. All right. So energy, forces, and motion. That's what physics is all about, and we're going to be talking all about physics here. So let me see where we want to go with all these lessons. Covering energy, forces, and motion. My hope is that I find a good way to lead you guys through some labs. It's not nearly as exciting watching me do the lab, which is always why I had you guys doing the hands-on with the labs. And very few times would I just sit up in front of the class and do like a demo type of lab for you. But unfortunately, in the position that we're in, that's kind of where we're going to have to go. So I'm going to do some labs like that. There may be some times where you have things at home that you can do with the labs, especially with physics. It's a lot easier than chemistry when we don't have chemicals that we need necessarily. So we're going to do physics using some things that you have at home. You're going to watch me do some of the physics here. We're going to do some more of these packets. I know they're not the most fun thing in the world, but these packets that I'm sharing with you, hopefully you can see already, we've done 2 of them physics related, 2 packets physics related. And hopefully what you can see is that there is a lot of good information in there. And I think the information is kind of laid out in a way that it's fairly easy to understand. At least I haven't gotten a whole bunch of questions related to those packets. Maybe you guys just aren't asking the questions yet. A few questions, but not too many. But I think that the packets lay the information out for you so that it at least gives us a point where we can talk about. And that's what we're going to do today. We're going to talk about that first packet. Let me see if there's anything else. No, we're going to do some math problems related to physics and how physics are involved in things around us all the time. All right, so that's it. So I'm going to cut the video here. What I want you to do, I'm going to pause here. Pause. Did you guys think I was really paused there? I tried to make it look like I was really paused. So anyway, I want you to pause your video here, and I want you to open up your measuring motion packet that you finished. It looks like most everyone finished that packet by now. So measuring motion, I want you to pause the video here. I want you to open up your packet, and then you're going to have the video going with your packet open so that you can check your answers as I move along. I'm going to put the paper up on the screen for you. I'm going to share my screen, and I'm going to put the document up on the screen. So as we go through, you can see what I'm talking about. All right. I'm not going to go in a lot of in-depth conversation with this because it's just me talking to the camera, and I don't really know what you need necessarily. So open up your measuring motion packet, pause the video, and then unpause when you're ready to roll. All right. See you guys when you get back. Welcome back, peeps. Let me pull up your measuring motion document. There we go. All right, I'll get rid of this down here, get that out of our way. I'm enjoying this song right now, by the way. I saw this on the Global Citizen concert. Maybe you guys watched it. I thought this was a pretty good song. So make sure you have your measuring motion document where you can see it, or at least you can watch this video and then go back and add things to it. All right, there we go. So your objectives for this short little video lesson, I'm going to make it as short as possible anyway, is what is motion? We're going to talk about that, which we already have a little bit. How is motion shown by a graph? What are speed and velocity? And what is acceleration? So I'm going to go through my document. I have the answers posted so you can follow through on my document and then take a look at the answers that you have. Really what I want you to make sure that you do is that you have your document so that you can put any notes on there. If you missed something, if you got something wrong, then I want you to mark it. Make sure that you understand. I'm going to do the best that I can to explain. It doesn't always translate well to a video, at least not as well as it does when it's live and I'm standing in front of you. But I want you to make sure that you understand if you missed something, why you missed it. And then even through the explanation of this video, if you still don't understand, please contact me and ask questions. Some of you have already started asking me questions, but I know that some of you still aren't comfortable asking questions. But it's especially important when we're doing lessons like this because you're not going to see a lot more on this topic that we would normally see while we were in class. So for you to best understand it, you're going to have to ask some questions. So let's start going through your measuring motion packet. I'm going to go right to the questions. I'm not going to read the packet to you. I know that you guys can read. Question number 1. What is the purpose of a reference point? We talked about this in one of your warm-ups. The purpose of the reference point is to determine if an object is in motion. They give you 2 pictures here. The picture on the left, you see the balloon in front of the mountains, and then the picture on the right, what you should see is that the mountains are still in the relatively same position in the picture. I see a little bit of difference there, but it's relatively the same position in the picture, but the balloon is now positioned over top of the mountains. And that's supposed to show you that the balloon has moved. There is motion taking place with that hot air balloon. And number 2, the question says, what is the fixed reference point in the photos? So that would be the mountains. The mountains are a fixed point. They don't move. And then you can see that the balloon moves above the mountains. Let's go down here. All right, this was a little confusing to some people, so hopefully I'll be able to lead you through it here. First thing that you need to know is that there was a paper on Owen's desk. It started with Owen. So Owen is the origin or the reference point of the paper. It was on his desk to begin with, so that's the origin. That's where it started. All right, so that's that part of it. And then I also wanted to talk you through this part because this may be confusing to some people. But this is like as if it were on a graph. Now we have it down here where it shows more of this is like a graph viewpoint. But I also want to show you like up where the desks are. So what you need to understand is that if you have a graph, you have the 2 axes on a graph. You have the y-axis and the x-axis. The y-axis would be going vertically up and down here. I'm trying to move my mouse. Hopefully everybody can see me moving that there. So that is the y-axis. It goes vertical. The horizontal axis is the x-axis. And if you think, because when you look down here, it says positive and negative. If you're moving up the axis, going from the 0 point, the 0 point's always going to be down here where the 2 axes meet. So at the 0 point, if you move up the y-axis, that's positive. If you go down the y-axis, that's negative. If you go to the right, if you move to the right on the x-axis, that's going to be positive. If you move back to the left on the x-axis, that's going to be negative. So again, if you think right here, let me go down here and make more sense. If you think right here at the 0 point, it should make more sense what I'm talking about. If I'm moving up the y-axis, then my numbers are increasing. It's positive. If I'm moving down my y-axis, the numbers are getting smaller, so that's negative. If I go up on my x-axis, which is my horizontal axis, if I go up, that the numbers are getting higher, so that's positive. If I go down, the numbers are getting smaller, so that's negative. All right, so let's go back up here so we can kind of go over the units that it's talking about. So again, my origin or my reference point right here is Owen. The paper starts on Owen's desk, and it goes from Owen to Lupe. There we go. From Owen to Lupe. So that is going 1 positive unit on the y-axis. I'm going up the y-axis 1 unit, so 1 desk. So that's 1 positive unit. Now I'm on the x-axis because the x-axis is horizontal. So I go from Lupe to Maya, from Maya to Jeff. So that is going 2 positive units on the x-axis. Then I go down 2 units on the y-axis, and then I go to the left on the x-axis, which would also be negative. So negative 1, 2, 3, -3 places on the x-axis. All right, so that's what this is telling you. 3 negative units on the x-axis. So that was the last one there. Okay, so that's what that means when we're looking at the positive and negative units on the x and y axes. Okay, so now this one was a little tricky for some people, but it says number 4 says, what is the shortest path that the paper could take to return to Owen's desk? The shortest path, and it cannot move diagonally. So I'll tell you my answer. My answer was to go 1 positive unit on the y-axis going to Jamal and 1 positive unit on the x-axis to Owen. So let's go back up to the desks, and I'll show you what I was talking about. All right, so the paper is here with Lewis. If I go 1 positive unit on the y-axis right here, the paper would go to Jamal. And then now I'm back on my x-axis because I'm trying to get back to Owen. So I'm going to go 1 positive unit on the x-axis to Owen. You could also go from Lewis to Eva. So 1 positive unit on the x-axis and then 1 positive unit back to Owen on the y-axis. You could also do it that way. So it wasn't asking you for the paper to take the path that it started on, like to reverse the path. It wasn't asking you to do that to get back to Owen. It wanted the shortest path. So again, as long as you understand the directions and how, like what that means, positive unit, x-axis, positive unit, y-axis, and so on. As long as you understand that, I'm cool with that. And if you don't understand, please ask me. So there's number 4. All right, so let's go down to number 5. By the way, I want to tell you guys, this is the second time that I'm going through this entire worksheet because the first time I was doing this, I thought it was recording and it wasn't. So now here I am doing it all over again, which the reason I'm telling you that is because I want you to keep your head up. I want you to keep doing your thing. Things are going to go wrong sometimes. You got to do it again. All right. Anyway, number 5, the average flight speed of a bald eagle is about 50 kilometers per hour. A scientist has measured an eagle flying 80 kilometers per hour. How is this possible? First of all, speed. When we're talking about speed, most often we're going to be talking about an average speed. So total distance divided by total time. Here's my equation. Average speed, total distance divided by total time. Most often, that's what we're going to be talking about. Occasionally, we may have some problems where we're doing instantaneous speed, but most often we're going to be talking about average speed. So my answer, because it says, how is this possible? My answer is it's possible because the average is 50 kilometers per hour, but most objects do not travel at a constant speed, meaning it's not the same speed the entire time. It may go, the bald eagle may move as fast as 80 kilometers per hour, but that was an instantaneous speed. So at that very moment that the scientists measured that speed, it was 80 kilometers per hour. The bald eagle was flying at 80 kilometers per hour. But it may go slower than 50 kilometers per hour. So it may fly, like, let's say 20 kilometers per hour. It can go a lot slower than that. 50 kilometers per hour is the average. So that's how it's possible. And then within our text here, it gave us an example. So if we're going to calculate average speed, again, it's total distance divided by total time. In this case, when it's talking about somebody walking down the hall, the person walked, maybe you, it says you can use the equation. It takes you. Yeah, it takes you. So you were walking down the hall and you went 4 meters and it took you 2 seconds to walk that 4 meters. And if you do the math, 4 meters divided by 2 seconds, you were walking at 2 meters per second right here. That's where it shows you that. And then we have another problem related to the same thing. So for you to practice, suppose you walk 10 meters down a hallway. So I'm on number 6 here, the math focus. Suppose you walk 10 meters down a hallway in 2.5 seconds. What is your average speed? Show your work. So again, average speed, I first write my equation. Average speed equals distance divided by time. And then I plug my numbers in. 10 meters is my distance divided by 2.5 seconds is my time. If I divide, I have we are walking at 4 meters per second. That's how we got that. Okay. The units, if you think back to when we did density and we had our units for density, this works the same kind of way. So if I have distance in meters and I have time in seconds, I have to have both of those units in my answer. They do not cancel one another out because they are not like units. So that's the way math works. If I do not have like units, they have to both be in the answer. So that would be meters divided by seconds, meters per second, 4 meters per second. And you guys are going to get some practice with that too. Okay, so this one, the graph that I did ended up being a little bit messy because in order for me to get rid of this mess, I was going to have to start all over, and I didn't want to start all over. So this is a little bit messy, but you're going to get the point. So how can you show speed on a graph? So let's look at number 7. Suppose you have a dog that walks at a constant speed the whole way. On the graph, draw a line showing that the dog walks at a constant speed during the walk. Now, some of you, when I looked at your papers, some of you, I'm over here on the graph here. Some of you gave me a line that went flat across. So just flat across. So for example, like if you were at 3 meters and you put your line, you stayed at 3 meters the entire time. So what that would mean, if your line was flat across, that means that the dog isn't walking. Your position, meaning the distance, is 3 meters. So in the beginning, the dog was at 3 meters. And at the end, the dog was still at 3 meters if your line was flat across, or wherever you put your line at 2 meters or whatever. If the line is flat, the distance is not changing. If the distance is not changing, that means that the dog was not moving. If you notice this red line, I have it on the diagonal, and I attempted, now again, it's not real pretty, but I attempted to have it going the same distance in the same amount of time. So for every 1 second, my seconds are on my x-axis down here at the bottom. I go from 0 to 1 second, 1 second to 2 seconds, 2 seconds to 3 seconds, and so on. What I attempted to do with this line to show you was that every second that passes, second of time, the dog would walk 1 meter. So the easiest one to see for me here is like right about in here. So you could see that from 3 seconds to 4 seconds, I go from 3 meters to 4 meters. 3 seconds to 4 seconds, I go 3 meters to 4 meters. That's 1 second and 1 meter. All right. Now look at my explanation down here. See the line I added to the graph. The dog walking at a constant speed would mean that the dog walks the same distance in the same amount of time. On a graph, that would be a straight diagonal line. For every second that passes, the dog would walk 1 meter. And that's what I attempted to show you here. Okay, so again, you may want to pause the video here so that you can look at my explanation and the line that I put on here if you don't understand. You just need to make sure that you're, if you put the flat line on your graph to show me, that you understand why that's incorrect. All right. Let's go to number 8. We're talking about velocity. All right, so first of all, my definition is right here for velocity. Velocity is the speed of an object and its direction. All right, speed and direction. Number 8, someone tells you that the velocity of a car is 55 miles per hour. Is this correct? Explain. It is not correct. And the reason it is not correct is because over here my definition tells me that velocity is the speed of an object and its direction. So velocity would include the direction along with the speed. Here it says someone tells you that the velocity of a car is 55 miles per hour. That would just be the speed, 55 miles per hour. So that's an example of speed. There is no direction there. In order for it to be velocity, it would have to be 55 miles per hour north or 55 miles per hour south, 55 miles per hour east, west, whatever. But it has to have a direction on there. If you have speed and direction, that's velocity. All right, let's skip on down. There was a table here that you had to fill in some information. Okay, so it was talking about velocity. And remember, with velocity, we have direction and we have speed. Velocity changes when speed changes, when direction changes, or when both speed and direction change. All right, so if speed changes, the direction changes, or both change, that would be a change in velocity. So it gives you a situation over here, and then it asks you to label what changes. The raindrop falling faster and faster, the speed changes. And we know that because it says faster and faster. So the speed changes. You guys can read through these examples, but the one that I wanted to point out here, because it's a little tricky, especially if you don't have a reference of driving a car, even though you've all been in a car. Car taking an exit off of a highway. When you exit a highway, typically you're going to slow down. At least I hope you slow down. If you don't, you're probably going to be in trouble. So the speed is going to change and the direction is going to change because we're veering off of the highway. So speed and direction there. All right, but now let's go down to where we had to fill something in. The baseball hit by a batter. When a baseball is hit by the bat, the speed of the ball is going to change. The ball is not going to leave the bat at the same speed as the pitcher throws it. So the baseball hit by the batter is a change in speed and change in direction because we're going to send the baseball back the opposite direction that it's thrown in, hopefully, if you hit it. All right. And then here you were supposed to give me, there was what changes speed and direction, and you're supposed to give me an example of that. Like I think I saw a couple people put things like leaves from a tree blowing across the ground or something like that. So the speed and the direction of the leaves blowing across the ground would change. So that would be a change in velocity. Whatever example you gave. Number 10. We are talking about acceleration. So let's look over here in the text at the definition of acceleration. Acceleration is how quickly velocity changes. Remember, velocity is speed and direction. So a change in one or both of those things would be considered acceleration. If I change my speed, that's acceleration. Whether the speed is increasing or decreasing, that's still acceleration. A change in direction would also be acceleration. So if I am moving south and then I start moving to the east, that's a change in direction. That would be considered acceleration. Because a lot of people think that acceleration is just by moving faster. That's not the case. And we may label it differently. We may call it negative acceleration or deceleration, but it's still a form of acceleration. So number 10 says, is the cyclist accelerating and how do you know? So if you look over here at the pictures, the cyclist is going at a speed of 1 meter per second, and then the speed keeps increasing, 2 meters per second, and then 3 meters per second, 4 meters per second, and 5 meters per second. And then you also see that over here at 5 meters per second, they're trying to make it blurry just to represent that the cyclist is going faster. And if you read the caption, the cyclist moves faster and faster as she pedals her bike south. So we have speed and we have direction. That would be velocity. Is the cyclist accelerating? How do you know? Yes, the cyclist is accelerating, and I know because the speed is changing. So even though the cyclist, he or she, is moving south the entire time, so the direction does not change, but you can see that the speed is increasing, and therefore that is acceleration. It would also be considered acceleration as the cyclist starts to press the brakes and slow down. So going from 5 meters per second to 3 meters per second to 2 meters per second, that's also acceleration, but we're going to call that negative acceleration or deceleration. So any change in speed, any change in velocity, which is a change in speed or direction, is acceleration. We will get to talking about the units for acceleration. We'll talk about that, but I'm gonna wait on that because this video is gonna get really long if I start to get into that. Okay, number 11. What happens to an object when it is negative acceleration? The speed is decreasing. So if it's negative acceleration, we're slowing down. Same thing. All right, let's take a look at this graph. Is number 12, is the slope positive or negative when the car's speed increases? Is the slope positive or negative when the car's speed decreases? If you think back to when we were talking about the graph before, and I was talking about the X and the Y axis, if I move up the Y axis is over here on my left side, is the vertical axis, goes up and down. If I go up the y-axis, that is positive. If I go down the y-axis, it's negative. If I go up the x-axis is the horizontal axis here. In this case, it's time. If I go up the x-axis, that's positive. If I go down the x-axis, that's negative. Okay, so back to my question. Is the slope positive or negative when the car's speed increases? So as I move along here, the slope is positive as the speed increases. Speed is right here. So as I go from 0 meters per second all the way up to 5 meters per second, you can see that my slope is increasing. It's going up. So as the speed goes up, the slope goes up. And then it flattens out right here. But then at 7 seconds, I am at 5 meters per second at 7 seconds. Then it says, is the slope positive or negative when the car speed decreases? I go from 5 meters per second down to 3 meters per second right here. 5 meters per second, go down to 3 meters per second. The slope is going down, so that's negative. All right, I'm going down the y-axis. That's negative. Okay, so the slope would be negative. As the car's, here's my answer. As the car's speed increases, the slope is positive. As the car's speed decreases, the slope is negative. Review. You have your vocab there. You have acceleration, speed, motion, velocity. Make sure that you review those things. Make sure that you understand the difference, what they are. Number 1, what is the difference between speed and velocity? We talked about this. Velocity is speed with direction. So the difference between speed and velocity is that velocity would also include a direction. Fill in the graphic organizer for a car that starts from one stop sign and approaches the next stop sign. And then it gives you 4 terms that it wanted you to use. So here I am at a stop sign, and then I'm going to move to my next stop sign. So when I am at my stop sign and I begin to move, that is positive acceleration. I'm beginning to move faster. So even if I'm going in a straight line, it's going to be positive acceleration because I'm going to start to go faster. Eventually, I'm going to get to a point where my speed stays the same. So that's going to be a constant velocity. I'm going in a straight line. I'm not turning in any direction. So the velocity doesn't change with the direction. And I'm going to go at a constant speed. So that's a constant velocity. When I start to approach the next stop sign, you need to start slowing down. That's deceleration. I'm going to slow down. And then when I get to that stop sign, I'm going to come to a rest. So I'm at rest right here. Number 3, describe the motion of the skateboard using the graph below. Write what the skateboard does from time 0 seconds to time 40 seconds. All right, so I'm going to read my answer, but then I'm going to be over here on the graph so you can see what it is that I'm talking about. So again, I have my y-axis, which is my position. That's my distance. And then my x-axis is my time. So I go from 0 up to 40 seconds. All right, so it wants me to describe what's happening from when 0 seconds at the beginning to 40 seconds at the end. The skateboard from 0 seconds right here up to 15 seconds, the skateboard positively accelerates. So I'm going from 0 up to 30 meters. So it's positive acceleration there. And I'm actually moving once I get up to whatever speed I'm going to travel at. You could also say that because I am traveling the same distance in the same amount of time, that my speed remains constant there. All right. So, but I have to go from 0 up to 30. So positive acceleration from 0 to 15 seconds. From 15 seconds, which is right here, to 20 seconds, the skateboard does not move. So this is what we were talking about. If you had with the dog above, like with that problem earlier, if your line was flat, then there's no movement there. It's staying at the same distance. So here I'm at 30 meters. So at 15 seconds, I'm at 30 meters. And then at 20 seconds, I'm still at 30 meters, which means that the skateboard didn't move during that time. All right. And then from 20 seconds up to 30 seconds, again, there was positive acceleration. The skateboard started to move. There was positive acceleration there. And then from at 30 seconds to 40 seconds, there is deceleration or negative acceleration. And then at 40 seconds, the skateboard stops. So at 30 seconds, I'm at 40 meters, and then it goes down to 0 again at 40 seconds. Okay. So the other thing that you can see, even though the line is going down, and I'm not moving up to that 50-meter mark. Basically, what I'm doing is the skateboard is returning to where it started. So I'm at 40 meters, and I go back to the 0-meter mark, which means that I traveled, even in this space right here, I traveled 40 meters. So you have that. All right, number 4. The graph above shows that the skateboard went a total distance. You know what? I'm going back up here now because now I'm rethinking. The skateboarder went from 40 meters to 0. So it traveled 40 meters and it did it in 10 seconds. So that would be acceleration also. But I can see why you would give it to me either way. And I got to be honest with you, I'm just now thinking about that as I'm talking this through. Okay. So that could be acceleration also, because the skateboarder is actually going faster because you went 40 meters at 40 meters down to 0. So traveled 40 meters and did it in 10 seconds. So that's actually acceleration. Anyway, so you could give it to me either way and I would accept it, but technically you would be accelerating. All right, so let's go to number 4. I probably just confused everybody with that because I kind of confused myself, and then I worked it out in my head. That's what we do, science. All right, number 4. Calculate that the graph above shows that the skateboard went a total distance of 80 meters. Let me show you how we got that. Okay, so over here it started at 0. And then we went up and flattened out and went up again and went to 40 meters. Okay, so went out 40 meters. You can think like you went down the street 40 meters. And then basically what you did is you turned around and came back and went another 40 meters. So that's 80 meters. Okay, so that's where you got the total distance. So when a total distance of 80 meters, what was the average speed of the skateboard? So again, the way that you show your work in this class is that you write your equation, you plug in your numbers, and then you solve. So average speed equals distance divided by time. That's my equation. My average speed in this problem would be 80 meters, my total distance, and did it in 40 seconds. That's my total time. So 80 meters divided by 40 seconds, my average speed is 2 meters per second. As we talked about before, with my units, if they are not like units, then they both must be in the answer. And I have my division sign, but the way that we read that is per. So 2 meters per second. That's the way we get that. All right, peeps. So if you feel like any of this was confusing to you, I got confused a couple times as I was going through this. If you feel like any of it is confusing, then I want you to make sure that you ask me questions. Another song that I saw on Global Citizen. I have no idea what he's saying. Hopefully it's clean. All right, so make sure that you ask me questions, and I will do my best to lead you through it. Sometimes it's better if we do it live, but I'm trying to do this video so everybody can watch it when they get a chance to watch it. So check your measuring motion document, go over your answers, ask questions if you have any questions. You guys stay awesome. I miss you and I love you. See ya.